Welcome to our presentation on the visualization of big data from social networks via the visualization program Gephi. What you can see in the background is the final output of our very own analysis and visualization of a social network for which we used Gephi. We will walk you through the steps of how we got there and why it is important to use Gephi for this analysis later in the presentation. Before starting with the content, I would quickly like to introduce the team that has been working on this presentation. They are Stefan Embrichtinger, Michael Wild, Max Meyer, Sebastian Stöckers, and myself, Paul Nuschele, which have worked on this additional group project for the course Data Analytics at ESADE. Now, going into detail. In today's presentation, we will cover the following topics. First of all, we will provide an overview of social network analysis and the basics of network theory. Second, we will introduce Gephi, its tools and functionalities. And last but not least, we want to show how we use Gephi, give you a real-life demonstration, and how we analyze the subsample of a Facebook social network to create a targeted social media marketing campaign. First of all, to talk about network theory. Network theory is basically the study of complex interacting systems that can be represented as graphs. A graph is a bunch of nodes connected by edges. For example, you have person A, B, and C representing each of them a node. If you look at the background, you can also see nodes and edges. Highlighted at the moment is the orange node, which is connected with a lot of lines, the so-called edges. Graphs can be both undirected and directed. A great example are Facebook friendships. Facebook friendships are undirected. On the other hand, if one person likes, for example, a famous actor, the page of a famous actor, it will be a directed link. The two most common networks are biological networks and social networks. When we talk about biological networks, the most famous ones are, for example, the neuron web and the food web. The biological neural network is a series of interconnected neurons in the human brain. It is the interface through which neurons interact with their neighbors, usually consists of several axon terminals connected via synapses to dendrites on other neurons. This is actually an example of when Gephi was used to illustrate on how different synapses in the human brain are connected. On the other hand, a food web is the natural interconnection of food chains and generally a graphical representation of what eats what in an ecological community. Even though Gephi is not used for this representation, food webs are an integral part of biological networks. As a second important part, we have social networks. The most important ones hereby are social media networks, collaboration graphs, and for example graphs about disease transmission. Hereby we also can give an example of the Ebola outbreak of 2014. This graph shows the worldwide air transportation network. Each link represents a passenger flux between a pair of airports. In total, this network contains approximately 4,000 airports and 25,000 links. This representation was made possible by the very strict requirements on safety and healthcare. Due to the Ebola outbreak, every single person that got in contact with Ebola, first of all patients and second of all also doctors, had to be registered, and also their movements had to be registered. Therefore, you could actually really see how doctors and patients have been traveling via airplanes throughout the world. Coming to the second part of our presentation, I quickly want to give you a brief overview of Gephi, what it can do, and its tools and functionalities. Talking about Gephi. Gephi is an open source application to both visualize and explore data, including complex analysis of links and social networks for a greater understanding of data relationships. Gephi is equipped with quite a lot of tools and functionalities. First of all, it offers you a visualization of graphs. This visualization happens in real time, so you can see immediately how different algorithms reshape your social network. Gephi can cope with networks of up to 100,000 nodes and 1 million edges. An integral part of Gephi are the so-called layout algorithms, which give shapes to the graphs. They are state-of-the-art algorithms for both efficiency and quality. These force-based algorithms force the nodes and edges into different directions, form and make apparent the different clusters and modularities, and are optimized for graph readability. Another important part of Gephi are the incorporated metrics and statistics, the most common ones for social network analysis. For example, there's the shortest path. The shortest path problem is the problem of finding a path between two nodes in a graph such that the sum of the weights of its constituent edges is minimized. Furthermore, there are also various centrality measures, for example based on degree, betweenness, and eigenvector. A high centrality measure normally means that a node has large influence on the transfer of items or beliefs through the network. Closeness, clustering coefficients, and community detection are a measure of the degree to which nodes in a graph tend to cluster together. Furthermore, there's the PageRank algorithm, an iterative algorithm that measures the importance of each node within the network. Coming to the third part of this presentation, which is actually a real-life demonstration of how we use Gephi to analyze a social network in Facebook, and then how we continue to implement a targeted social media marketing campaign. Intuitively, when you look at this marketing campaign, you see these three large nodes. Intuitively, we would pick the largest nodes for our social media campaign. However, I want to show you now how we got there and why Gephi has been so helpful in the process. When we think about targeted social media marketing, the following question arises. What is important? How do I make my campaign effective and efficient? Who are the persons to contact? And most importantly, who has influence in this social network? Thereby, we rely on an important paper by Errol and Walker from 2012, which was named Identifying Influential and Susceptible Members of Social Networks. In their paper, Errol and Walker claim that social media marketing is all about contagion. They basically identify two members in a social network. First of all, influential individuals who catalyze the diffusion of opinions, behaviors, innovations, and products in networks like Facebook, LinkedIn, or Twitter. These opinions can be about politics, products, or also vacations. Influential users exercise influence on susceptible members and susceptible individuals in the network that can be guided into a certain direction or change in opinion by influential users. Going a little bit more into depth of this paper, there are a couple of things we have to take into account, a couple of mitigations to their findings. First of all, they say we have to look out for homophily, which is basically the trend that we tend to look for or have friends with common interests. Another mitigating effect are confounding effects, which is the tendency of connected members to be exposed to same external stimuli, which is only a natural thing that if considering you have friends who share your interests, you normally also get influenced by, for example, the same sport or the same sports star. Going a little bit deeper into the actual findings, we can see the following. First of all, you see in dark gray the influence of different groups, and in light green the susceptibility. An important finding hereby is, for example, that men are more influential than their female counterparts. When we look, for example, at the Facebook relationship status, we can also see that married couples are the least susceptible and that they are also the most influential, quickly followed by single people. Using these findings of Errol and Walker, we went further and wanted to analyze our own dataset with the goal of identifying the influential members in our network. Thereby, we relied on a network by Stanford University, which is created for research purposes. Looking at the network in the beginning, we can see this bunch of nodes and edges slumped together without allowing for any useful analysis. The basic dataset statistics tell us that this network consists of around 4,000 nodes, so around 4,000 Facebook persons, and around 88,000 edges, which means 88,000 connections between these 4,000 individuals in our network. To actually start to make sense of this network, we were running a couple of statistics. We started off with a modularity report, which basically tells us how many communities, how many clusters are in this network. Thereby, we identified 17 different networks. As you can see in this size distribution, we have modularity classes and clusters of different sizes. For example, modularity class 10 and 15 are our largest clusters, whereas modularity classes 3, 4, 5, and 7 are rather small communities. Each community gets a different color, which you can already see a little bit in the background. Going further, we also look at the eigenvector centrality, which basically tells us how much influence on the transfer of items through the network a certain node has. A score of 1 means that a person has a lot of influence. A score of 0 means exactly the opposite. Looking at this statistic, we can immediately see that only very few nodes have a very high score, giving them influence in the network. We basically get the same picture with the degree distribution, which basically means how many edges or ties one node has. We basically can identify around 4 to 5 nodes which have a high degree distribution. Going further, I want to show you how we got to the final output. Remember, in the beginning, everything was just this gray bunch of various nodes. Going a little bit more into depth now, we can see in the first example when we applied the modularity classes and gave the graph some color. And the next step, we started to run the force-based algorithm, which forces the communities together, and it already gives a little bit better example of this presentation. In the next part, we can actually see how the force-based algorithm works live, drawing the communities closer together and giving the graph some real shape. This is the final output after around 4 to 5 minutes of running our algorithm. What you can see are the different clusters, for example, the larger ones, the light blue one in the right bottom or the orange one in the top part. What you can also see are already relatively large nodes. I want to highlight these in a second. Looking at, for example, the purple one on the left, the green one in the middle, and the blue one on the right, we can see that these are the most influential members in our network. Why is this important? It is important because it helps us to achieve our ultimate goal. We want a targeted and effective social media marketing by identifying the influential members whom we want to spread the information in our network. Who is this useful for? First of all, for marketing departments in startups, but also larger corporations. Furthermore, it is also useful for academia, for researchers who can analyze the spread of trends, or thinking about the current Brexit, the spread of beliefs, for example, in politics. To conclude, I hope that we were able to provide you with some interesting insights on social network analysis, Gephi, and its functionalities and tools, and how you could use Gephi for your very own targeted social media marketing campaign.